The morning fog hung dense across the Ardennes forest on December 23, 1944. At 06:45 hours, a battery of 4 German 105mm light field howitzers from the 2nd Panzer Division's artillery regiment prepared to fire a support mission. The battery occupied a position in a tree line approximately 4 kilometers behind German forward positions near Bastogne, Belgium. The guns had been in position for 3 hours, carefully sighted with overhead concealment from tree branches to defeat aerial observation. The battery commander, a Hauptmann with 2 years of Eastern Front experience, gave the fire order. His crews had rehearsed the drill countless times. Load, aim, fire. 3 rounds per gun. 12 shells total would arc toward American positions defending the approaches to Bastogne. The entire fire mission would take less than 90 seconds. Then the battery would displace immediately to a secondary position 500 meters away. This was standard doctrine, refined through years of combat against Soviet artillery. Fire briefly, move quickly, survive. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The crews fired their first salvo at 06:46. The howitzers recoiled, brass casings ejected, loaders rammed fresh rounds into breeches. Second salvo at 06:47. Third salvo at 06:48. The battery commander ordered ceasefire. Gun crews immediately began displacement procedures. Unhook the trail spades, secure remaining ammunition, start the stair trucks that would tow the guns to the alternate position. At 06:49, 30 seconds after the last German shell left the barrel, the first American shells arrived. But these were not ordinary artillery rounds. The German crews heard no warning whistle, no time to dive for foxholes. The shells detonated 15 meters above the tree line in a pattern of perfect air bursts that blanketed the entire battery position. 12 rounds impacted within a 3-second window. Every detonation occurred in the air, sending fragments down through the overhead concealment that the Germans had carefully arranged, fragments that shredded canvas, punctured fuel tanks, and cut through human tissue with surgical efficiency. The first salvo killed 3 crew members and destroyed 1 howitzer. The second salvo, arriving 20 seconds later, killed the battery commander and 4 more soldiers. The third salvo destroyed 2 more howitzers and the ammunition truck. Elapsed time from the last German round fired to the final American shells landing was 2 minutes and 15 seconds. The battery ceased to exist as a combat unit. For gun silent, 11 men dead, 17 wounded. The survivors who could still move abandoned the position and fled into the forest. This was not an exceptional event. This pattern repeated itself across the Ardennes throughout late December 1944, January 1945. German artillery batteries that fired at American positions found themselves under devastating counterfire within minutes, often before they could complete displacement procedures. The American shells arrived as airbursts that detonated overhead with no ground impact, defeating the foxholes and trenches that German doctrine said would provide protection. German artillery officers who had survived years of combat on the Eastern Front against Soviet artillery, who had fought in North Africa against British guns, reported that they had never encountered anything like the American counterfire system that emerged in December 1944. The difference was a weapon that had been developed in absolute secrecy for 4 years and had been withheld from ground combat operations in Europe until the emergency of the German Ardennes offensive forced its release. The weapon was called the proximity fuse, and it transformed artillery from an area suppression weapon into a precision killing system. Combined with the American Fire Direction Center system that could locate enemy guns and deliver massed fires within minutes. The proximity fuse created a counter-battery capability that German artillery had no defense against. The story of how this weapon was developed, why it was kept secret, and how it changed artillery warfare in the final months of World War II reveals the intersection of scientific innovation, military doctrine, and industrial production that characterized American military effectiveness. The proximity fuse was not a minor improvement to existing technology. It was a revolution in how artillery functioned, and German soldiers caught in its blast radius learned that the rules of artillery warfare had changed in ways that made survival nearly impossible. To understand why the proximity fuse was so devastating, you must first understand how artillery had worked for the previous 30 years, and why the airborne detonation it provided was fundamentally different from anything that had come before. Artillery shells in 1944 used two types of fuses. Contact fuses detonated when the shell struck something solid, typically the ground. Time fuses detonated after a preset delay, allowing the shell to burst in the air if the delay was calculated correctly. Both types had severe limitations. Contact fuses detonated on the surface, which meant their fragments traveled primarily horizontally or upward. Troops in foxholes or trenches with any overhead cover were relatively protected. The fragments that would have hit them were blocked by the earth walls of their fighting positions or by logs and sandbags placed over the top. Time fuses could produce airbursts, but setting them required complex calculations. The Fire Direction Center had to compute not just range and azimuth to the target, but also time of flight for the shell. Time of flight varied with range, propellant temperature, barrel wear, wind conditions, and atmospheric density. Get the calculation wrong by even half a second, and the shell might burst too high to be effective or might impact the ground like a contact fuse. Even when calculations were correct, time fuses were inconsistent. Manufacturing variations meant fuses set for identical delay times might detonate several seconds apart. Achieving effective airbursts across an entire battery salvo required careful preparation, precise meteorological data, and experienced fire direction personnel. The proximity fuse eliminated all these calculations. The fuse contained a miniature radio transmitter and receiver powered by a battery activated by the centrifugal force of the shell's spin when fired. As the shell descended toward the target, the radio waves transmitted by the fuse reflected off the ground. The receiver measured the frequency shift of the returning signal, a phenomenon called Doppler effect. When a reflected signal indicated the shell was at optimal burst height, typically 15 to 20 meters above the surface, the fuse triggered detonation automatically. Every shell became an airburst. No calculation required. No time, fuse setting needed. No variation in detonation height. Every round in a salvo detonated at the same optimal altitude, regardless of where each shell originated or what trajectory it followed. The fragments from these airbursts traveled downward and outward in a cone pattern that was far more lethal than surface bursts. Troops in foxholes that would survive contact fuse shells had no protection against fragments coming from above. Trenches with overhead cover were less effective because fragments penetrated light overhead protection. Artillery pieces themselves were vulnerable because fragments struck from above, hitting crew members who might be shielded from horizontal fragments by the gun shields. The weapon had been conceived in 1939 by British scientists working on radar. Dr. William Butemant at the Royal Naval Scientific Service in Britain had proposed a radio proximity fuse for anti-aircraft shells. The concept was that aircraft presented difficult targets for anti-aircraft guns because a shell had to detonate very close to the aircraft to cause damage. Contact was nearly impossible. Time fuses required impossibly precise predictions of where a maneuvering aircraft would be when the shell arrived. A fuse that could detect proximity to the aircraft and detonate automatically would vastly improve anti-aircraft effectiveness. The British passed the concept to American scientists in September 1940 when Britain shared radar and other sensitive technologies as part of the Technological Exchange Agreement. American scientists at the Department of Terrestrial Magnetism at the Carnegie Institution in Washington took up the challenge. The National Defense Research Committee, created in June 1940 to coordinate military research, funded the project. Section T of the NDRC, headed by Dr. Merle Tuve, took responsibility for development. The technical challenges were enormous. The fuse had to fit inside an artillery shell, which meant it had to be small, no more than a few inches long and a few inches in diameter. It had to survive being fired from a gun, which subjected it to accelerations of 20,000 times the force of gravity. It had to work reliably after experiencing that shock, which was severe enough to shatter most electronic components. It had to generate radio waves, receive reflected signals, process those signals to determine altitude, and trigger detonation, all within the few seconds the shell was in flight. And it had to be manufacturable in quantities of millions at cost low enough that artillery could use them routinely rather than reserving them for special missions. Dr. Tuve and his team worked through 1940 and 1941 developing prototype designs. They tested hundreds of variations of vacuum tubes, which were the only electronic amplification technology available at the time. Vacuum tubes were fragile glass devices that shattered under normal artillery acceleration. The team developed rugged vacuum tubes with reinforced internal structures that could survive firing. They miniaturized radio transmitters and receivers to fit inside the constrained space. They designed battery systems activated by the centrifugal force of the shell's rotation so the electronics would not draw power during storage. By mid-1942, working prototypes existed. The United States Navy conducted tests firing proximity-fused anti-aircraft shells at target drones. The results were dramatically better than conventional time-fused shells. A proximity-fused shell might destroy a target drone with a single shot. Conventional shells typically required dozens of rounds to achieve a hit. The Navy immediately ordered production for anti-aircraft use aboard ships. The fuse entered combat in January 1943 when the cruiser USS Helena used proximity-fused 5-inch anti-aircraft shells against Japanese aircraft during the Battle of Rennell Island in the Solomon Islands. The effectiveness was immediately apparent. Ships equipped with proximity fuses shot down Japanese aircraft at rates far exceeding ships using conventional ammunition. By mid-1943, proximity fuses were standard equipment for the Navy's anti-aircraft batteries. The Army had been watching Navy results and wanted proximity fuses for field artillery. The potential for ground combat was obvious. Air-bursting shells would be far more effective against troops and equipment than contact fused shells. The Army ordered development of fuses for standard artillery calibers, 105mm and 155mm. By late 1943, fuses were being manufactured in quantity. The Crosley Corporation, a radio manufacturer in Cincinnati, Ohio, produced fuses under contract. Other companies joined production. By mid-1944, factories were producing proximity fuses at rates exceeding 100,000 per month. But the fuses were not used in Europe. General Dwight Eisenhower, Supreme Commander of Allied forces in Europe, had received explicit instructions that proximity fuses were not to be used in ground combat on the European continent. The restriction came from the highest levels of American command and was based on a single fear. If the Germans captured intact fuses from unexploded shells, they might reverse engineer the technology. German electronic engineering was highly sophisticated. American intelligence believed Germany could develop copies of the fuse if they had access to a working example. Even more dangerous, Germany might develop countermeasures that would defeat the fuse, rendering it useless. The greatest fear was that Germany would develop proximity fuse technology for anti-aircraft shells and deploy it against Allied bombers over Germany. American and British strategic bombing campaigns depended on bomber formations flying in tight patterns for mutual defensive fire. Proximity-fused anti-aircraft shells that detonated automatically near aircraft would be far more deadly than existing time-fused shells. The losses to bomber formations could become unsustainable. The strategic bombing campaign, which was already costly in crew lives and aircraft, might become impossible. So the fuses were withheld from European ground combat, even though they were available in large quantities and even though field commanders wanted them. The Pacific theater was different. Islands that were captured by American forces remained in American hands. Any unexploded shells containing proximity fuses would be recovered by American troops, not captured by the enemy. The Marines and Army used proximity fuses extensively in Pacific Island operations. The effectiveness was documented in battle after battle. Japanese troops in trenches and bunkers that would have survived conventional artillery bombardment were devastated by airbursting proximity fused shells. In Europe, American artillery continued using contact and time fuses through the Normandy invasion, the breakout from Normandy, the liberation of France, and the advance toward Germany in autumn 1944. American artillery was already the most effective artillery system in the world due to the fire direction center system, graphical firing tables, excellent communications, and trained forward observers. But the artillery was still using conventional fuses with all their limitations. Then on December 16, 1944, Germany launched Operation Wacht am Rhein, the offensive that became known as the Battle of the Bulge. 28 German divisions, including elite Panzer and Panzer Grenadier formations, attacked through the Ardennes forest, striking a weakly held sector of the American line. The attack achieved tactical surprise. American intelligence had failed to detect the buildup. German forces broke through American positions in multiple locations, creating a bulge in the Allied lines that threatened to reach the Meuse River and potentially split Allied forces. The situation was critical. American forces rushed reinforcements to contain the penetration. The 101st Airborne Division, recuperating in France after Operation Market Garden, was trucked to Bastogne, a critical road junction that the Germans needed to sustain their advance. Artillery battalions displaced northward to support the defense. The weather was overcast, grounding Allied air power that would normally have devastated German columns on the move. For several days, American forces fought to contain the German advance using ground forces alone. On December 19, 1944, General Eisenhower formally requested authorization to use proximity fuses in ground combat. The request went to General George Marshall, Chief of Staff of the Army, and to Secretary of War Henry Stimson. The case was urgent. American forces were under severe pressure. Every weapon available was needed to stop the German offensive. The risk of proximity fuses being captured and reverse engineered was outweighed by the immediate need to defeat the German attack. Authorization was granted on December 21, 1944. All restrictions on proximity fuse use in ground combat were lifted. Shells were rushed from depots to artillery units along the entire front. The first artillery units to receive proximity fuses were those supporting the defense of Bastogne and the northern shoulder of the German penetration near Elsenborn Ridge. Stockpiles of shells arrived by truck convoy on December 22nd. Fire direction centers received brief instructions on employment. The technical operation was simple. Proximity fuse shells required no special calculations. Load them, fire them, they would airburst automatically. The only restriction was a minimum range of 300 meters to prevent shells from detonating too close to friendly positions. American artillery crews fired their first proximity fused missions on December 22nd and 23rd. The results exceeded expectations. German infantry attacking across open ground toward American positions encountered devastating fire. Shells detonated overhead with no warning. There were no impact craters for troops to shelter in, no safe ground. Every shell in a salvo detonated at optimal height, creating overlapping fragment patterns that left no gaps in coverage. Colonel Oscar Alfred Axelson, commanding the 406th Field Artillery Group near Monschau, Germany, had actually used proximity fuses 2 days earlier without authorization. Axelson commanded long tom battalions, 155mm guns with ranges exceeding 20 kilometers. His units supported the defense of the northern shoulder where German attacks were intense. On December 20th, German infantry assaulted American positions. Axelson ordered his batteries to fire proximity fuse shells that had been in storage awaiting authorization. The airbursts shattered the German attack. Axelson's unauthorized decision proved correct, and when formal authorization came through the next day, his units were already experienced in employing the new ammunition. The psychological impact on German troops was severe and immediate. German infantry doctrine emphasized entrenchment. Soldiers were trained that properly constructed foxholes with overhead cover provided protection against artillery. A foxhole 2 meters deep with logs and earth overhead would protect against anything except a direct hit. This doctrine had been validated through years of combat on the Eastern Front against Soviet artillery. German soldiers trusted their field fortifications because those fortifications had kept them alive through countless bombardments. Proximity fused shells made those fortifications obsolete. A shell detonating 20 meters overhead sent fragments downward through the lightest overhead cover. Logs that would stop horizontal fragments were penetrated by fragments traveling downward with high velocity. German soldiers discovered that taking cover in a foxhole provided no protection and might actually concentrate casualties as multiple soldiers in adjacent positions were hit by the same airburst. Some German units reported that soldiers refused to take cover during artillery bombardment, reasoning they had equal chance of survival standing in the open versus crouching in a foxhole. This was not accurate. Foxholes still provided some protection, but the perception revealed the psychological impact. When established doctrine proved ineffective, when procedures that had worked for years suddenly failed, unit cohesion degraded. Soldiers lost confidence in their training and their leaders. German tactical reports from late December 1944 and January 1945 consistently mentioned the new American artillery fuse. Reports described shells that burst in the air without requiring ranging shots, shells that detonated at consistent height regardless of terrain, and devastating effectiveness against troops in field fortifications. Some reports initially speculated that Americans were using some new type of time fuse with greatly improved accuracy. Others correctly identified that the shells were using some form of automatic proximity detection. German intelligence services attempted to recover intact fuses from unexploded shells. The recovery effort faced immediate problems. Proximity fuses had very low dud rates. The reliability achieved through years of development meant that more than 98% of shells functioned as designed. The few duds that did occur typically had damaged fuse components from impact, making analysis difficult. German technical intelligence did recover some fuse components by January 1945, and analysis revealed the radio proximity detection principle. But by then, Germany lacked the industrial capacity to develop countermeasures or copy the technology. Factories were under constant bombing, raw materials were scarce, and technical personnel were being drafted for combat duty. The American fear that Germany would reverse engineer proximity fuses and deploy them against Allied bombers proved unfounded. Even if Germany had possessed complete technical documentation and unlimited samples, German industry in early 1945 could not have manufactured complex electronics in the quantities required. Germany was struggling to produce basic ammunition and fuel. Sophisticated radio fuses were beyond available capacity. But for German artillery crews, the immediate problem was not analyzing American technology. The problem was a surviving American counterbattery fire that now arrived faster and more accurately than ever before. The American counterbattery system had been refined throughout 1944. Target acquisition methods included sound ranging, flash spotting, aerial observation, and radar. The SCR 584 radar could track artillery shells in flight and calculate backwards to determine gun location. Multiple intelligence sources fed data to Corps and Division Fire Direction Centers that maintained detailed maps showing known and suspected enemy artillery positions. When German guns fired, American detection systems located them within minutes. Fire Direction Centers calculated firing data and assigned available batteries to engage. With proximity fuses, the counter-battery fire was far more deadly. Airbursts against artillery positions were devastating. Gun crews that might survive near misses from contact fused shells were killed by airbursts detonating overhead. Artillery pieces themselves were more easily damaged because fragments struck from above, hitting vulnerable components like sights, recoil mechanisms, and ammunition storage. The timing became critical. German doctrine for counter-battery survivability emphasized rapid displacement. Fire a brief mission, 3 to 5 rounds, then immediately hook guns to prime movers and displace to alternate positions. The entire displacement procedure, if executed perfectly, required 12 to 15 minutes for motorized artillery, longer for horse-drawn batteries. German artillery officers knew from experience fighting Soviet artillery that if they could complete displacement in under 20 minutes, they would usually escape counter-battery fire. Against American counter-battery fire with proximity fuses in December 1944 and January 1945, displacement in 20 minutes was too slow. American target acquisition typically located German guns within 5 minutes of initial firing. Fire direction centers computed firing solutions and broadcast them to assigned batteries within 2 minutes. Shells were in flight within 8 to 10 minutes of the German battery's first round. Total time from German gun firing to American shells landing was often under 12 minutes, sometimes under 10 minutes. German crews firing their 3 to 5 round mission would use approximately 2 minutes for the actual firing. That left 10 minutes for displacement if they were to escape before American counter-battery fire arrived. Unhooking trail spades, connecting prime movers, loading ammunition, and beginning movement required at least 8 to 10 minutes under good conditions. Under combat stress, in darkness, in mud or snow, displacement took longer. German batteries frequently found themselves under fire before displacement was complete. Crews caught in the open hitching guns to trucks were killed by airburst shells that detonated overhead with no warning. The lethality of proximity fuse counter-battery fire was documented in American after-action reports and German unit records. The 2nd Panzer Division Artillery Regiment, which entered the Ardennes offensive with 36 guns, reported by early January that effective artillery strength was reduced by more than 50% due to losses from American counter-battery fire. These losses were not primarily from guns destroyed by direct hits. Most losses came from crews killed or wounded by airbursting shells while guns were still serviceable. A battery that lost its commander and half its crew could not function even if the guns were undamaged. The 12th SS Panzer Division Hitlerjugend, fighting on the northern shoulder near Elsenborn Ridge, reported that American artillery fire was the decisive factor preventing successful attacks. Division reports noted that assembly areas came under devastating fire that arrived with no warning, that airbursts made foxholes ineffective, and that artillery positions could not be maintained in the same location for more than one brief fire mission before coming under accurate counter-battery fire. German artillery ammunition expenditure dropped dramatically during the Battle of the Bulge. Not because ammunition supplies improved, they were still constrained by logistical problems, but because German artillery officers were reluctant to reveal their positions by firing. Every fire mission invited devastating American response. German battery commanders had to weigh whether providing fire support justified the near certainty that the battery would be engaged by American counter-battery fire within minutes. Some German batteries adopted extreme shoot and scoot tactics. Fire 1 or 2 rounds only, then immediately displace regardless of whether the mission was complete. This kept batteries alive longer, but made artillery support fragmentary and ineffective. American forward observers reported during the Bulge that German artillery fire was sporadic and limited compared to earlier campaigns. This was not due to lack of guns. Significant German artillery remained in the field, but the guns could not be used effectively without being destroyed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The effectiveness of proximity fuses multiplied when combined with time-on-target missions. Time-on-target procedures had been standard American artillery doctrine since 1943. The Fire Direction Center calculated not just firing data, but also time of flight for each battery's shells. Batteries were ordered to fire at staggered times so that all shells arrived over the target simultaneously. The effect was devastating against any target, but against artillery positions with proximity fused shells, time-on-target missions became annihilation events. A German battery detected firing by American sound, ranging, or aerial observation would be engaged by multiple American battalions. The Fire Direction Center might assign 3 or 4 battalions, 48 to 64 guns, to the counter-battery mission. Each battalion would be given firing data calculated for time on target. All shells would be proximity fused. The American batteries would fire at computed times, shells from distant batteries launching first, shells from closer batteries launching later, all timed to arrive together. The German battery, having completed its fire mission, would be in the early stages of displacement. Crews would be in the open, some connecting prime movers, others loading ammunition, the battery commander coordinating movement. There would be no warning. The first indication of incoming fire would be the sound of shells passing overhead, a sound that lasted less than a second before the detonations began. 60 shells detonating simultaneously in airbursts 20 meters above the battery position. The fragment pattern would cover several hundred square meters. Every crew member in the open would be hit. Vehicles would be shredded. Ammunition stocks would detonate. In 3 seconds, a battery that had existed as a functioning military unit would cease to exist. Survivors of such strikes, when there were survivors, consistently reported the same experience. No warning, no time to take cover, instantaneous devastation. The speed and violence were beyond anything they had encountered on the Eastern Front or in earlier fighting in the West. Some survivors refused to return to artillery duty, claiming they would rather serve in infantry positions where they at least could see the enemy and had some chance to fight back. German artillery officers who were captured and interrogated by American intelligence after the Battle of the Bulge provided detailed assessments of American artillery effectiveness. These assessments, preserved in interrogation reports at the National Archives, are remarkably consistent. German officers acknowledged that American artillery had been superior throughout the campaign due to better fire control, more abundant ammunition, and greater mobility. But they stated that the introduction of the airbursting fuse in late December fundamentally changed the nature of artillery warfare. One German artillery Hauptmann captured in January 1945 told interrogators that German counter-battery doctrine had been based on the assumption that approximately 20% of incoming shells would be effective against a properly dispersed and entrenched battery position. Contact fused shells that impacted away from guns or crew positions caused no damage. Time-fused airbursts that detonated too high or too low were similarly ineffective. A dispersed battery might survive even a substantial counter-battery strike with limited losses, then displace and continue operations. With proximity-fused shells, the Hauptmann said, effectiveness approached 100%. Every shell became an airburst at optimal height. Every shell that landed anywhere within the battery position caused casualties or damage. There was no ineffective fire. A counter-battery strike with proximity-fused shells would destroy or neutralize any battery engaged. The only survival option was to not be there when the shells arrived, which meant displacement had to be complete before counter-battery fire could be delivered. Given American target acquisition and fire direction capabilities, displacement in under 10 minutes was required. This was impossible for horse-drawn artillery and barely possible for motorized artillery under ideal conditions. Under combat conditions, in winter weather, in darkness, displacement in under 10 minutes was unrealistic. Therefore, the Hauptmann concluded German artillery could not operate effectively against American forces once proximity fuses were introduced. This assessment, from a professional artillery officer with years of combat experience, represented the German artillery's recognition that they had been tactically defeated. Not defeated because German guns were inferior, they were excellent weapons. Not defeated because German crews were poorly trained, German artillery training was rigorous and thorough. Defeated because the American system of target acquisition, fire direction, and ammunition technology created a capability that German doctrine had no answer for. The effectiveness of proximity fuses was not limited to counter-battery fire. Against infantry and armor, the results were equally devastating. The 2nd Infantry Division, defending positions near Krinkelt and Rochrath in the path of the main German armored thrust, fired proximity fuse shells in direct support missions throughout late December. German infantry attacking across snow-covered fields encountered airbursts that detonated above them with mechanical precision. The casualty rates were so high that German commanders reported attacks could not be sustained. The 1st SS Panzer Division Leibstandard Adolf Hitler, attacking toward the Meuse River in the southern sector of the Bulge, encountered proximity fused artillery fire beginning December 23. Division records note that American artillery fire caused severe casualties among Panzer Grenadier infantry attempting to advance in support of tanks. The airbursting shells were particularly effective against troops in half-tracks and trucks, where thin armor provided no protection against fragments coming from above. German armor was more resistant to artillery fragments than infantry, but proximity fuses still increased effectiveness against tanks and self-propelled guns. Airbursts could damage external equipment, vision blocks, radios, and expose crew members. A tank with damaged vision blocks was blind. A tank with a damaged radio was cut off from command. Even if the tank itself remained mobile and its main gun functional, its combat effectiveness was degraded. More critically, proximity-fused artillery suppressed German armor by making it dangerous to operate with hatches open. Tank commanders in combat typically rode with their head out of the turret hatch to maintain situational awareness. Button up completely and visibility dropped dramatically, but riding with hatches open during artillery bombardment had always been dangerous. With contact-fused shells, a tank commander might risk it, calculating that the odds of a direct hit on the turret were low. With proximity-fused shells detonating overhead, exposed tank commanders were killed regularly. German armor began operating buttoned up, which reduced their effectiveness significantly. The cumulative impact on German offensive capability during the Battle of the Bulge was significant. Historical analysis of the battle identifies multiple factors in the German failure. Allied air power, once weather cleared after December 23rd, hammered German columns. American armored reinforcements, particularly the 3rd Armored Division and 2nd Armored Division, struck German spearheads effectively. Fuel shortages prevented German tanks from sustaining the advance. Determined American infantry defense, particularly at Bastogne and St. Vith, disrupted German timetables. But American artillery was the constant factor that degraded German operations throughout the battle. Artillery hit German assembly areas before attacks began. Artillery engaged German columns on the move. Artillery provided defensive fires that broke German infantry assaults. And artillery conducted counter-battery fire that suppressed German guns to the point where German artillery support became minimal. The proximity fuse was the technological edge that made this artillery dominance overwhelming. Without proximity fuses, American artillery would still have been superior due to better fire direction and greater ammunition supply. But German forces could have operated more effectively. German artillery could have provided more support, and German casualties would have been lower. The proximity fuse turned American artillery from a superior system into a dominant system that German forces had no effective response to. By early January 1945, as the Battle of the Bulge ended with German forces retreating eastward, proximity fuses were standard ammunition throughout American artillery units in Europe. Shells were manufactured in quantity and distributed to forward ammunition dumps. Fire direction centers planned proximity fused fires as routine missions rather than special weapons. The tactical impact was that American forces advanced with confidence that artillery support would be devastatingly effective against any target. The final months of the war in Europe, from January through May 1945, saw American and Allied forces advance from the German border to the heart of Germany itself. Artillery played a central role in every phase of this advance. The crossing of the Rhine, the encirclement of the Ruhr, the drive across central Germany, all were supported by massive artillery preparations using proximity fused shells extensively. German forces defending prepared positions along the West Wall fortifications encountered proximity fused bombardments that were far more effective than conventional artillery against fortified bunkers. Airbursts could not penetrate the thick concrete of the bunkers themselves, but airbursts devastated trenches, communication routes, and open fighting positions around the bunkers. Defenders attempting to move between positions were caught in the open by airbursts. Infantry attempting to counterattack out of bunkers were hit before they could deploy. The effectiveness was quantified in ammunition expenditure reports. American artillery fired millions of proximity fused shells in the last 4 months of the war. The proportion of proximity fused to contact fused ammunition varied by mission type, but for missions against troops in the open or in field fortifications, proximity fused ammunition became the preferred choice. Fire direction centers would specify proximity fused ammunition when available because the effectiveness justified the higher cost per round. The cost differential was significant. A proximity fuse cost approximately $18 to manufacture in 1945, compared to less than $2 for a conventional contact or time fuse. The complete round, shell plus fuse plus propellant, cost approximately $35 for a proximity fused 105mm shell versus about $20 for a conventional round. But tactical commanders considered the additional cost justified. A mission requiring 100 proximity fuse rounds to achieve desired effect might require 300 or 400 conventional rounds. The overall cost and ammunition expended was lower with proximity fuses despite the higher per round cost. Production capacity was never a limiting factor. American factories produced proximity fuses at rates exceeding 200,000 per month by early 1945. This production supported both European theater demands and Pacific theater operations. The industrial system that had produced millions of trucks, thousands of aircraft, and vast quantities of conventional ammunition adapted to produce sophisticated electronics in similar quantities. The manufacturing techniques developed for mass production of radio fuses, including automated testing and quality control procedures, represented significant engineering achievements in their own right. The Germans never developed effective countermeasures. German electronic warfare efforts focused on radar jamming and radio intercept, areas where Germany had technical expertise. But proximity fuses operated on frequencies and at power levels that made jamming impractical. The fuses functioned for only a few seconds during shell flight, making intercept and analysis difficult. Even if German forces could detect the fuse transmissions, there was no tactical response available. You could not shoot down an incoming shell based on detecting its fuse signal. Some German technical intelligence reports from early 1945 proposed countermeasures, such as dispersing metallic chaff to confuse the fuse altimeters or using smoke screens to potentially interfere with radio reflections. None of these proposals were ever tested operationally. Germany lacked the resources to develop, manufacture, and deploy such countermeasures in the quantities that would be required to protect widespread troop formations and artillery positions. The German Army's response to proximity fuses was therefore tactical rather than technical. Disperse more widely, move more frequently, attack at night when American aerial observation was reduced, limit artillery activity to brief, essential missions. These were sound tactical responses given the constraints, but they were defensive measures that reduced German operational effectiveness. An army that must constantly hide from enemy observation and artillery is an army with limited offensive capability. The Japanese army encountered proximity fused American artillery in the Pacific theater earlier than German forces faced it in Europe. By mid-1943, proximity fuses were being used in island operations where there was no risk of intact fuses falling into enemy hands permanently. Japanese forces on Saipan, Guam, Tinian, Polilliu, Iwo Jima, and Okinawa all experienced proximity-fused artillery bombardment. Japanese tactical responses evolved through these campaigns as commanders learned that conventional defensive procedures were inadequate. On Okinawa in April through June 1945, Japanese artillery adopted extreme concealment measures. Guns were positioned in caves and tunnels cut into limestone hillsides. Crews would roll guns forward to firing positions, fire 1 or 2 rounds, then immediately withdraw into the tunnels before American counter-battery fire could arrive. This preserved the guns and crews, but made sustained artillery support impossible. Japanese artillery on Okinawa fired far fewer rounds per gun than in earlier campaigns because any gun that revealed its position by sustained firing would be destroyed within minutes. American counter-battery procedures on Okinawa were highly refined. Sound ranging units with multiple microphone arrays could triangulate gun positions to within 50 meters. Aerial observers in L-4 Cubs and Marine OY observation aircraft patrolled constantly when weather permitted. The SCR-584 counter-battery radar could track Japanese shells in flight and compute firing positions. Fire direction centers had detailed maps showing every cave entrance, every ravine, every terrain feature that might conceal artillery. When Japanese guns fired, target location was rapid and counter-battery fire followed within minutes, always with proximity-fused shells. The effectiveness of American counter-battery fire on Okinawa was documented in Japanese prisoner interrogations and capture documents. Japanese artillery officers reported that crew casualties from American counter-battery fire were severe, that guns could not be operated from open positions under any circumstances, and that ammunition resupply to cave positions was nearly impossible during daylight due to American observation aircraft. The Japanese 32nd Army Artillery on Okinawa fired approximately 45,000 rounds during the 82-day battle, an average of 550 rounds per day for an army that initially possessed more than 200 artillery pieces. This expenditure rate was far below what would be expected for a defensive battle of such intensity and reflected the inability of Japanese artillery to operate effectively against American counter-battery fire. The European theater, where proximity fuses arrived in December 1944, saw even more dramatic effects because German forces were more dependent on artillery than Japanese forces. German military doctrine emphasized combined arms coordination with artillery, providing the foundation for both offensive and defensive operations. Infantry attacks were preceded by artillery preparation. Defensive positions were supported by artillery that could deliver fires on predetermined target areas. Counterattacks required artillery to suppress enemy positions while assault forces maneuvered. When German artillery could not function effectively, the entire tactical system degraded. The final defensive battles in Germany from February through April 1945 showed this clearly. German forces defending the Rhine crossings, the Ruhr pocket, and the final approaches to Berlin had prepared elaborate defensive positions with carefully registered artillery concentrations. But American artillery superiority, magnified by proximity fuses, meant that German defensive fires were suppressed or eliminated before they could affect American attacks. The crossing of the Rhine River at Remagen in March 1945 provided a case study in artillery effectiveness. When American forces of the 9th Armored Division unexpectedly captured the Ludendorff Railroad Bridge intact on March 7th, German forces attempted to destroy the bridge and eliminate the American bridgehead on the East Bank. German artillery had good observation of the bridge from hills on the East Bank and could range the entire bridgehead area. Under normal circumstances, concentrated German artillery fire would have made the bridgehead untenable and would have destroyed the bridge through sustained bombardment. American counter-battery fire prevented this. Within hours of the bridge capture, American sound ranging units and aerial observers had located German artillery positions. American Corps artillery, including 8-inch howitzers and long-tom 155mm guns, engaged German batteries with proximity fused counter-battery fire. German batteries that attempted to fire on the bridge were hit by devastating airbursts within minutes. By March 8th, German artillery fire on the bridge had been reduced to sporadic harassment. American engineers were able to strengthen the bridge and construct pontoon bridges nearby with minimal interference from German artillery. The bridgehead expanded rapidly because American forces could operate without effective German artillery opposition. Field Marshal Albert Kesselring, who took command of German forces in the West in March 1945 after Field Marshal Gerd von Rundstedt was relieved, reported to Hitler that American artillery superiority was absolute and that German artillery could not provide effective support. Kesselring had commanded German forces in Italy for 2 years and had extensive experience fighting American and British forces. His assessment that the situation in early 1945 was qualitatively worse than earlier campaigns reflected the impact of proximity fuses on an already superior American artillery system. The quantitative impact of proximity fuses can be estimated from casualty data and ammunition expenditure records. American artillery in Europe fired approximately 20 million rounds from January through May 1945. The proportion of proximity fused ammunition varied, but averaged approximately 20 to 30% of total expenditure, meaning 4 to 6 million proximity fused rounds were fired. These rounds were concentrated in missions against personnel rather than against fortifications or vehicles, which meant they accounted for a disproportionate share of casualties inflicted by artillery. Studies conducted by the United States Army after the war estimated that proximity fused shells caused 3 to 4 times the casualties per round compared to contact fused shells when used against troops in field fortifications. This multiplication factor varied with target type and terrain, but was consistently documented across multiple analyses. Applied to the 4 to 6 million proximity fused rounds fired, this suggests that proximity fuses increased total artillery effectiveness by approximately 40 to 60% compared to what would have been achieved with conventional ammunition alone. German casualties from all causes in the final 4 months of the war were approximately 600,000 killed and wounded on the Western Front. Artillery caused approximately 60 to 70% of all casualties in World War II combat, which suggests artillery was responsible for roughly 400,000 German casualties in this period. If proximity fuses increased artillery effectiveness by 50%, then approximately 130,000 German casualties can be attributed specifically to the enhanced lethality of proximity fused shells compared to conventional ammunition. This calculation is necessarily approximate, but it illustrates the scale of impact. Proximity fuses, introduced in late December 1944, killed or wounded more German soldiers in 4 months than many entire battles in earlier periods of the war. The weapon was not a minor technical improvement. It was a fundamental change in artillery effectiveness that German forces had no defense against. The technological achievement represented by the proximity fuse was remarkable for its time. The fuse contained 5 vacuum tubes, numerous resistors and capacitors, a battery, an antenna, and a detonator mechanism, all packaged in a cylindrical housing approximately 3 inches in diameter and 5 inches long that could survive being fired from a gun at accelerations exceeding 20,000 times gravity. The electronics had to function reliably after this shock, generate and receive radio signals, process those signals to determine altitude above ground, and trigger detonation at the optimal moment, all within the 3 to 5 seconds the shell was in flight. Manufacturing this device in quantities of millions required industrial processes that did not exist before the war. Vacuum tubes had to be manufactured with reinforced internal structures to survive gun launch. Assembly procedures had to be developed that could produce fuses rapidly while maintaining quality control. Testing procedures had to verify function of every fuse because a single dud could mean casualties from ineffective fire or from shells landing short among friendly troops. The industrial achievement was comparable to other major manufacturing programs like aircraft production or tank production, but concentrated in a much smaller physical package. The proximity fuse program cost approximately $33 million in total development and testing from 1940 through 1943, equivalent to approximately $500 million in modern currency. This development cost was spread across more than 20 million fuses produced during the war, making the per-unit development cost negligible. The manufacturing cost per fuse declined from approximately $30 for early production to $18 by late 1944 as production processes improved and volumes increased. Compared to the tactical value delivered, the return on investment was extraordinary. The program demonstrated American capacity for rapid technological development and mass production. From concept in late 1939 to combat deployment in January 1943 was slightly over 3 years. From combat deployment in naval anti-aircraft use to mass production for field artillery was another year. From restricted use in the Pacific to unrestricted deployment in Europe was 2 more years, but the delay was policy rather than technical limitation. When a decision was made to deploy proximity fuses in European ground combat in December 1944, the industrial capacity existed to supply ammunition immediately in vast quantities. This pattern of development, testing, production, and deployment at scale characterized American weapons programs throughout World War II. The Manhattan Project that developed atomic weapons followed a similar trajectory of rapid development supported by massive industrial investment. Radar systems, from early warning radars to fire control radars to airborne intercept radars, were developed and produced in enormous quantities. The industrial base that could produce proximity fuses in millions could also produce complex electronic equipment for every other application that military effectiveness required. German technical intelligence officers who analyzed captured proximity fuses understood the technical principles involved. The radio altimeter concept was not mysterious. German engineers could have designed similar devices if given the requirement and resources. But Germany in 1943 and 1944 lacked the industrial capacity to manufacture sophisticated electronics in the quantities required for mass deployment. German industry was focused on producing tanks, aircraft, submarines, and conventional ammunition. Vacuum tube production was limited and focused on radar and communications equipment. Diverting industrial capacity to develop a new artillery fuse would have required reducing production of other critical systems. More fundamentally, Germany faced a different tactical situation than the United States. German artillery doctrine emphasized mobility and dispersion to survive on the Eastern Front against Soviet artillery that used massive preparatory bombardments. The German response was to keep guns hidden and moving. Improving shell lethality through proximity fuses would not have changed this fundamentally. Germany needed more guns, more ammunition, and more prime movers to improve artillery effectiveness. Sophisticated fuses were a lower priority than basic production volume. The Soviet Union received detailed technical information about American proximity fuses through Lend-Lease channels. Soviet representatives inspected American production facilities and received sample fuses for analysis. Soviet technical experts understood the capability and the manufacturing requirements. The Soviet Union did not develop indigenous proximity fuse production during World War II. Soviet industry was focused on maximizing production of basic weapons, tanks, artillery pieces, trucks, and ammunition in enormous quantities. Complex electronics requiring precision manufacturing were beyond Soviet industrial capability at the time. The Soviet approach to artillery effectiveness emphasized massing huge numbers of guns and firing massive ammunition expenditures to achieve results through volume rather than per round effectiveness. This difference in approach reflected different industrial capabilities and tactical requirements. The American Army could afford sophisticated ammunition because American industrial capacity could produce both quantity and quality. The Soviet Army needed quantity above all else and designed tactics around weapons that could be manufactured in vast numbers, even if they were not technologically sophisticated. Both approaches were effective within their respective contexts, but the American approach provided flexibility and effectiveness per round fired that other armies could not match. British forces received proximity fused ammunition through joint production arrangements. British artillery battalions serving under American command in the European theater had access to proximity fused shells from American ammunition stocks. British units operating independently under British command had more limited access because British production of proximity fuses was smaller scale than American production. British doctrine incorporated proximity fuses where available, but British artillery continued to rely primarily on conventional ammunition supplemented by proximity fuses for critical missions. The British developed proximity fuses independently through parallel research programs. British scientists working on the same problem as American researchers produced similar technical solutions. But British production capacity was focused on meeting immediate war requirements for conventional weapons, and British industry could not divert resources to mass production of sophisticated fuses without reducing output of other essential equipment. The pragmatic solution was to receive proximity fused ammunition from American production under Lend-Lease arrangements rather than building duplicate British production facilities. This coordination between Allied forces represented another American advantage. The industrial capacity to supply not only American forces, but also Allied forces with sophisticated weapons and equipment meant that Allied operations could be conducted with equipment superiority over Axis forces. British tanks might use British guns, but they operated with American radios. American trucks supplied British logistics, and American proximity fused shells increased effectiveness of British artillery. The cumulative effect of American industrial production supporting Allied forces across all domains created overwhelming material superiority. The proximity fuse remained classified after World War II ended in August 1945. Details of the technology were not released publicly until 1947, when declassification allowed discussion of the basic principles. Even then, specific technical details remained classified for years to prevent potential adversaries from developing similar capabilities. The Soviet Union developed proximity fuses for anti-aircraft use by the early 1950s through independent research. The technology spread gradually to other nations as electronic components became more widely available and technical knowledge diffused. Modern artillery shells use electronic fuses that are direct descendants of World War II proximity fuses. Contemporary fuses are more sophisticated, using laser range-finding or GPS guidance in addition to radio altimeters. But the fundamental concept of automatically sensing optimal burst height and detonating accordingly remains unchanged. Every modern army uses airburst ammunition because the effectiveness against troops and light vehicles is so much greater than ground burst ammunition. The World War II proximity fuse established airbursts as standard artillery doctrine worldwide. The men who developed the proximity fuse received limited public recognition. Dr. Merle Tuve, who directed the development program, continued working in scientific research after the war and became director of the Carnegie Institution's Department of Terrestrial Magnetism. He received various scientific awards and honors, but remained little known outside technical communities. The engineers and technicians who solved the manufacturing problems that enabled mass production, who designed testing procedures, who worked in factories producing millions of fuses, received no recognition at all. Their work was classified during the war and remained obscure afterward. The artillery crews who fired proximity fuse shells in combat did not know the technical details of how the fuses worked. They received brief instructions that these new shells would airburst automatically and should be used against troops and artillery positions. The crews loaded the shells, fired them, and observed the results. The devastating effectiveness was immediately obvious to anyone who witnessed proximity fused fire missions. German positions that would have required extensive bombardment with conventional ammunition could be suppressed or destroyed with far fewer proximity fused rounds. Forward observers who called for fire missions quickly learned to specify proximity fused ammunition when appropriate. Fire direction centers tracked availability and allocated proximity fuse shells based on target priority. High-value targets, enemy artillery, troop concentrations, and defensive positions receive proximity fused fires. Lower priority targets might receive conventional ammunition to conserve the more expensive proximity fused rounds. This allocation process was routine artillery procedure, no different from allocating different types of conventional ammunition based on target type. The institutional knowledge about proximity fuse employment was captured in field manuals and training documents produced during and after the war. The United States Army Field Artillery School at Fort Sill incorporated proximity fuse tactics into artillery officer training. Post-war manuals described optimal employment techniques, allocation procedures, and target selection criteria. This documentation ensured that tactical knowledge gained through combat experience was preserved and transmitted to future artillery officers. The proximity fuse provides an example of how technological innovation changes warfare. The weapon was not obvious or inevitable. Competent engineers in any industrial nation could have conceived of radio proximity fuses. The challenge was not concept but execution. Developing electronics that could survive gun launch, manufacturing those electronics in millions of units at cost that permitted mass deployment, and integrating the new ammunition into tactical doctrine so that artillery crews use it effectively. American success in this development was the result of institutional capabilities rather than individual genius. The National Defense Research Committee identified the requirement, funded research, and coordinated development. The armed forces, particularly the Navy initially and the Army subsequently, provided tactical requirements and feedback on prototype performance. Industrial corporations developed manufacturing processes and built production facilities. Artillery schools developed tactical doctrine and trained personnel. All these institutions worked together to move a concept from laboratory to battlefield in less than 5 years. German forces facing this weapon in combat experienced it as a sudden and fundamental shift in artillery effectiveness. Tactical procedures that had worked for years suddenly became inadequate. Foxholes offered insufficient protection. Displacement times that had been adequate were now too slow. Artillery could not be used effectively without being destroyed by counter-battery fire that was faster, more accurate, and more deadly than anything previously encountered. The psychological impact of fighting an enemy whose artillery could kill from above with no warning and no defense was severe on German morale in the final months of the war. The strategic impact was that American ground forces could advance with confidence that artillery support would be overwhelmingly effective. Infantry assaulting German positions knew that preparatory bombardment with proximity fuse shells would devastate defenders and that supporting artillery could suppress any German response. Armor advancing into German territory knew that German artillery attempting to engage them would be destroyed by American counter-battery fire within minutes. This confidence enabled aggressive operations with acceptable casualties, maintaining offensive momentum that kept German forces continuously retreating. The Battle of the Bulge, where proximity fuses were first used in Europe, ended in German defeat, not primarily because of the fuses, but because of multiple factors including American numerical superiority, Allied air power, German logistical failures, and determined American defense. But proximity fuses were a contributing factor in defeating German attacks, particularly in counter-battery operations that suppressed German artillery and in defensive fires that broke German infantry assaults. The weapon provided an edge that made American artillery even more dominant than it had been previously. The subsequent campaigns from January through May 1945 saw proximity fuses used routinely as standard ammunition. The Rhine crossings, the reduction of the Ruhr pocket, the drive across Germany, all were supported by artillery that used proximity fused ammunition extensively. German forces attempting to defend prepared positions found those positions untenable under proximity fused bombardment. German forces attempting counterattacks found their assault formations shattered by airbursts before they could engage American positions. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.